I want to talk about your cell membrane and hormones. Now, as I draw out this cell membrane, you should be able to tell me that the outside of the cell membrane is hydrophilic. This means that it is water-loving. It likes to be near water. And I should hope that you'd tell me that the inside of the membrane is hydrophobic. This means that it hates water. Now, this creates an interesting dynamic for the cell because it turns out that hydrophobic molecules can actually travel through membranes, but hydrophilic can't because they can't make it through that hydrophobic layer. So when we talk about hormones, this creates something very interesting because many of your hormones are traveling around in your bloodstream, right? They have to go from a cell and then they have to go into the blood and then they have to get to another cell. If it's a hydrophobic hormone, it's not going to have a very hard time getting across its cell membrane and then into the blood. But once it gets into the blood, it's hydrophobic. It does not like water. And guess what blood's made of? It's mostly made of water. So what's going to happen in that case is that this hydrophobic hormone is going to be surrounded by a carrier. And that carrier is going to be able to shuttle it as it moves through the bloodstream and eventually reaches its target cell. Once it reaches its target cell, the carrier can go away. Once it reaches its target cell, the carrier can go away, and then the molecule has a relatively easy time again crossing the cell membrane. Now, these carrier hormone interactions follow, again, the law of mass action. So there's a hormone in the unbound state and a carrier in the unbound state, and these have a reversible reaction where they enter their bound state. At this end, we have lots and lots and lots of hormones that are unbound. And that's going to shift it toward the bound state because it wants to reach equilibrium. By the time we get down here, we have a lot of carrier hormone complexes. So everybody's bound, and when everybody's bound, that actually shifts the reaction the other way and makes them let go of each other. Now, the ability of a hydrophobic hormone to cross the membrane means that its receptors are most often inside of the cell because they don't have to be outside of the cell. In fact, they'll actually go on and do, they'll change gene function and things like that. Now let's consider what happens if we've got a hydrophilic hormone. I'm going to actually leave the hydrophobics on here. So the hydrophilic hormone, I'm going to draw it in pink, can't cross the cell membrane very easily. But it'll get released in a vesicle or something. And it has an equally hard time crossing the blood. But once it's in the blood, it can travel freely from one end of the blood to the other, doesn't need any special carrier or anything like that. And now it's going to have to get out of this vessel. And by the time it reaches the cell membrane, it really doesn't want to go across one more membrane. That's just going to make it take longer. So instead what happens is that the receptors for these guys are on the outside of the cell so that they never have to enter the cell membrane because it's really hard for them to do. So not only is the transport of these hormones influenced by their structure, but also where their receptors are located.